Okay, so this today we are going to tidy up what we started last week, which was looking at optimizers. We talked about a whole lot of optimizers. Maybe by way of recap, even though we don't have so much time, I will still run us through it. So we talked about different optimizers and what optimizers do. When we started our training program, when we started this class at the beginning with linear regression, we just touched on the first optimizer, which I call it the grandfather of all the optimizers, which is a gradient descent. Well, here we have come to see that gradient descent is not the only optimization algorithm. There are many others, but most of them derive from gradient descent and basically are improvements over gradient descent. So we have the gradient descent, the grandfather itself, the full batch. Then you have the stochastic gradient descent, where you are taking a single row, a single data set, or data point rather, single sample for um each training loop, right? So that means a lot of training loops for a single epoch if the amount of data is large. So it's not very good for large data sets. It's not good for very large data sets. But the middle ground, which is the mini batch gradient descent, is where you now take a small subsample of the entire data set, and if you run a single training loop on that. The next training loop, you take another subsample. So that's a mini batch gradient descent, which is still called stochastic gradient descent anyway, but that is really what people use these days when you hear SGD, stochastic gradient descent. It's actually a mini batch, not a single sample. So that of course results in um, a more erratic, right, descent in the loss landscape, but it actually improves performance overall. And of course, it's better for very large data sets. We talked about momentum, which is an extra factor that you add into the standard stochastic gradient descent so that the rate of descent down that slope in the loss landscape is dependent not just on the size of the gradient, right? Or the magnitude of the gradient and the direction of gradient, but also on how fast the gradient is changing. So that's why it's called momentum. In other words, the history of how the gradient has been moving, the moving average, basically. So that also improved the stochastic gradient descent that we know. And then root mean square propagation is another side. It's not really um, from um, gradient descent per se. It's a whole different algorithm of its own, but um, it has its own challenges. But it of course uses moving average of squared gradients, unlike momentum that uses moving average of the gradients, right? Or the rate of change of the gradient. This one is using moving average of the square of the gradient. That's why it's called RMS. And we also have the Adam. So Adam is now a child of um, SGD with momentum and RMS drop. So he gets the best of both sides. And then um, Adam with weight decay, right? And then we saw that there are a bunch of other ones as well. We have a momentum type called Nesterov. So it's still momentum, but it's slightly different approach. It's slightly different formula for calculating it. And then we also have NADAM, which is the same Adam, but it is using a Nesterov momentum factor. And then other grad, which is really old, um, older than gradient descent, I believe, even. Yeah, so you can see that there's a lot of different optimizers. But we looked at the whole thing. It was essentially evolution from gradient descent all the way down to the Adam with weight decay, which is what is currently being used a lot. And we looked at all of the factors and everything. We also talked about learning rate and scheduling. The fact that you can actually keep changing learning rates as you are training your model around the loop, as you know, the loop is going around, you can actually change learning rate at specified intervals, at specified number of steps based on a strategy, which could be either time-based or step-based, right? Or exponential decay or linear decay. And then we talked about different kinds of schedulers. So these are all of them. There's cosine annealing as well, which uses a cosine curve. And then we even have a reduced learning rate on plateau. This one does not change learning rate until when your model flattens out and the loss doesn't change much anymore. And then it it triggers and drops the learning rate so that you can squeeze a little bit more, you know. Then we have cyclic. So more advanced ones, we talked about warm up, which is not really a learning rate. It's still a learning rate schedule in a way, but warm up is prepping for the beginning of training, and it's really used a lot where you are fine-tuning models, because if you don't warm up, you will destroy the previous pre-existing weights, right? In fine-tuning, you don't want to destroy pre-existing weights. You want to maintain them and just fine-tune the model on the additional data you want to add. Or if you want to do transfer learning, where you're not just using additional data to train the model, you take a piece of maybe you remove the uh, the final few layers and add your own layers so that you can do a different kind of classification problem. So we talked about all of those. So we are going to just go in and look at how would how we would do optimization. So I already have some pre-existing um, PyTorch Colab notebooks I had done, which I'll use as a starting point. But I will still look at, if possible, well, maybe we don't have enough time, so I'm not going to really do it all from scratch, right? Um, this I had already gone through this, right? This is when we're doing basics of PyTorch, and so we can see it how easy it is to create neural networks, right? And layers, input layers, hidden layers, output layers. So the problem we want to now solve here is we want to solve the exclusive OR problem, right? And plot a decision boundary around it. But this time around, we want to try out a lot of different optimizers. So you can see I stacked here a lot of optimizers. The stochastic gradient descent, all of them are available in Torch, RMS prop, momentum. So for momentum, you are actually just going to do the stochastic gradient descent, but you pass in a momentum value here, which 0.9 is a good value to use. And then the Nesterov is the same thing. It's also momentum stochastic gradient descent with momentum of 0.9, but we specified Nesterov is true to tell PyTorch to use Nesterov algorithm to calculate the momentum. And then the Adam, you just have an Adam. Now you notice that when we are doing this um, variable learning rates ones like Adam and RMS prop, you can see that learning rate actually drops by a factor of 10. For HGD, you typically will have learning rate 0.1, depending on the problem too, and the size of gradients, right? You could um, choose to go lower, okay, or even go higher. But at the starting point for SGD, if you want to train exactly as a model, exactly on that same data set, that same model on that same data set with Adam or RMS prop, you actually have to drop the learning rate by a factor of 10. So it's something, the factor of 10 is not a rule, it's just a rule of thumb, not a hard and fast rule. You know, it's not like, oh, but it gives you a good idea of where to start, because these are hyperparameters which you may not know where to start from. But from experience, one of the things you find is that all the Adam um you know ones, typically you will default values are good enough. So we have default values for the beta 1, which is 0.9, and beta 2, which is 0.99, or sometimes 0.98. So those are values for momentum, which you can see here when we're doing normal momentum using 0.9. So 0.9 for momentum, 0.99 for um, the RMS, the RMS in the RMS prop part of it. Okay, so other grad is here as well. You can see that also other delta. There's an other max. So these are all variants of other grad. And then R prop and then ASGD. So there's a whole lot of different optimizers. So what this is doing is just take a basic exclusive OR problem, and then we will see how fast it will train on this. So first thing is we'll plot decision boundary. So we'll bring in our NumPy, matplotlib, torch, and the torch NN module. Then there's a function here that I created because this is a simple two-dimensional data set x1, x2, right? Which we'll plot. And then we'll have the y, which is a class. So this allows us to plot decision boundary because it's a simple exclusive OR problem. So if I think we've gone through this before, but let me just go through it again. When you're plotting a decision boundary, remember what a decision boundary is. It's just a graph plot that draws a line around where decision should be, or where the separation between classes should be, right? That's what the decision boundary is basically. And if you plot it well, typically it will do like this, and then it will color one region from the other if it is, in this case, is um a two parameter um it's a two parameter model because we're just looking at the x1 and x2, and then the results, which is a result of exclusive OR. So it's just taking this and then it is going to plot a mesh grid, right? It will have a grid, and then the grid will also be plotted the actual points on the grid, which are the different values, right? And then um, a tensor is going to be made. Um, so if you want to plot it, this one is plotted, this function rather is designed to just take a PyTorch model. So it will use that model to make the predictions instead of actual predicted values. So that's more convenient because you just pass in the model. So here it actually does inference with the model and gets the predictions, and then it squeezes the predictions to one dimension or two dimensions, removes all extra empty dimensions, then reshapes it into the X shape, and it plots it against the Y. So you see a contour plot of X and Y and Z is done, where if Z is greater than 0.5, then you give alpha of 0.4, which is the transparency and all of that. Then you can also plot the losses. I have function here that plots the losses. That one we've been doing it. Then we also have a function here that plots the predicted value against the actual true values, so that you can see how far away it is. So those are just preparatory functions to help with this. Now, here I defined the data here as a simple exclusive OR list, right? But I'm going to improve this, right, with something we did already, which is we will add some noise to this exclusive OR because this one is just a single, this is one, two, three, four samples, essentially, right? Each of them having a different value. So you can train a model and it will be able to differentiate this, but how well? So what we will do now is we'll increase the number of records here to a much larger number, where we will load we'll load a lot of random noise around so that it won't be very clean. Because as it is now, you can see it is very clean. It's just for the 4 points, right? Where zero and zero is um 0. Then 1 and 0 is 1. Then 0 and 1 is 1. And then 1 and 1 is 0. So these are 4 exact points. It's easy to draw a decision boundary around these 4 single points. So it's not really challenging, for all of these optimizers, especially with I used a simple, remember I talked about NN sequential. So with NN sequential, if you look at this carefully, it defines just a two-layer network. The first layer, which is the hidden layer, right, has 2 inputs and 4 outputs. The 2 inputs, of course, correspond to the 2 features in X, the two X1 and X2 that we are using in the exclusive or truth table. By the way, this is what we call a truth table, even though I don't know if I have to go through this again, but just go and do some research. If you did a bit of logic before, you know what truth table means. Basically, a way to represent the logic, the logic um, operator here. And the logic operator here is XOR, which means either or, but not both. That's what XOR means. It's exclusive or. So that's why 0, 0, when both are 0, right? Then the result of exclusive or is false. Because remember I said either one or the other is a 1, not both. If both are zeros or both are ones, then it will give you a 0. That's why the first value of y corresponding to this first sample row is 0. The second value of y corresponding to this sample row, where one of them is 1, is is true, right? And then for this one too, this one is also true because only one of them is true. But this last one is false. That is 0 because both of them are true. So both cannot be true. But if you're using normal OR, 1 will still be 1. That one is linearly separable. So we could do that with a single neuron or a single perceptron. Okay, so NN sequential, like I mentioned last time when we were going through PyTorch, is just a simple way of stacking the different layers. And you can see here we actually have 2 layers, right? The first layer is made up of a linear layer, which is a fully connected layer. And then we have this activation function called elu, right? But maybe what I'll do is let me use relu because we've been talking relu all this while so that we don't get a bit confused. Elu is a different activation function. We've not talked about activation functions yet. Um, we'll talk about those next. So linear layer, a relu, right? Then the next linear layer, remember the ReLU doesn't change the number of outputs. The ReLU is just activation function attached to each of the neurons in this layer. Even though it's kind of shown as different here, but it's really part of this layer. Okay. So this layer has an output of 4 neurons. Those output of 4 neurons become the input to the next linear layer, right? And then you just have one output from that linear layer, and that passes through sigmoid activation. Okay. So if I were to draw this, right, it will kind of look like I don't think I have a drawing. Um, but this is the closest it will look like, right? Except that this one has 3 inputs. But that one would have 2 inputs, then one intermediate, and then one output. Maybe I'll do a sketch and I can do a sketch and add that later on. So yeah, so it's actually this is the representation of that. So let's say the inputs, I'm not going to draw them as big circles because I just, it's an input. It's not really a neuron per se, but you could also use a neuron to represent it, right? And then you have this is the hidden layer, right? This hidden layer has, it will have 4 layers, or sorry, 4 neurons. It will have 4 neurons. So that's the hidden layer. And then you would have um, a single output layer. So the single output layer is what does the actual prediction. of whether the output, whether it's 00 should be 0 or 00 should be 1. Okay, and that's this. And just like what we've been doing, these are fully connected layers. So you are going to actually have um, all of them connected. That way, that's what you have. That's what you have. So yeah. So each of these will connect to the output. And then each of the inputs will also connect to the each of these will also connect. So each input will connect to um, this out to this, right? So this is each of these will have two inputs, and then there are four outputs. There are four. So when you look at the whole layer, right, we're actually looking at the whole layer, not the individual neurons. Remember, the number of outputs from a layer will always correspond directly to the number of outputs in that layer. That's a very easy way to think about it. So this input, for example, is going to connect to all of the outputs, um, all of the neurons that form all the outputs of the hidden layer. So that's a fully connected. And the reason why I'm taking some time to do this is just to have an understanding. I know we are still kind of fresh at this, so it's good to allow everyone to, rethink it again, right? And you see how that goes. So that's it. So that's a neural network that is implemented there. So of course, it's easy to just throw that in here. Let me just throw that in here. So this is the network. It has two inputs, four outputs for the first hidden layer, and then the output layer has just one output, which I actually forgot to draw the output, but there should be an output here. So there should be an output here. So okay, so that's it. Now, so the improvement I want to add here is I'll increase the data sets here, but let's keep going. So if you plot a simple decision boundary here, you get this, right? This is decision boundary from the model that is untrained. I just created a model now. It's not been trained. You can see it's not doing a good job at all. It's just been initialized with random values initially. Okay. So now what we will do is, of course, we'll put in a training loop. Okay. And then in that training loop, we'll now see how well it does. So we start with a simple 1000 epochs. We choose different optimizers. So what this example is going to do is to train use all of these optimizers to train the same model. Of course, the model will be recreated from scratch so that you don't just, otherwise you'll be cheating subsequent earlier models because earlier models will do all of the hard work. So what we do here is we create a loss function, which is called the criterion, right? I call it loss function here, but you see it being called criterion um, in a lot of places. So this criterion is BCE loss. which is the binary cross entropy loss. Remember, when you're doing a classification problem that's a binary class, that is two classes, yes, no, true, false, right? 0, 1. You always use a binary cross entropy loss. So that's what we're using here. We didn't use mean square error. This is for a regression problem. So, and then of course, this is the list, the dictionary rather, that we are using to track all of the different um, loss curves for the different optimizers. Okay. Then to ensure that we always start at the same starting point for each optimizer, we first of all capture the original initial um, parameters, the initial values of all the parameters. We'll use this to always restart, recreate the model with that same initial parameter. And that's what is happening here, right? What's happening here is basically when we go into the training loop, this is now the training, this loop is not a training loop. This loop is just each optimizer that we want to try out. And that's in this list of optimizers that we have here. So, um, but at the beginning, you have to restore the model, right, back to the initial state, this initial set of parameters. And then you run, you set it into training mode, you initialize the loss array for this particular optimizer, and then you now go into the training loop. In this training loop, like I've already said before, it's not really, there's not a lot here, right? You do a forward prediction, just passing X training to the model. You run the loss calculation using the loss function. The loss function, in this case, the criterion, always takes the predicted value and then the original um, true values, right? And it compares, and from the loss function, you now do a loss dot backwards, right? That's typically how you train models with PyTorch. You use loss dot backwards to do backprop. But before doing that, you use optimizer dot zero grad just to use the optimizer to zero out all previously calculated gradients in case for some reason they were not, so that you do not corrupt the new values. And then we run optimizer the step. Optimizer the step will now use the new gradient that are calculated by this loss of backward and use it to update the parameters in each of the each of the layers in the model. And then you can now append all these. These are additional collecting data so that you can plot. Then after all of this is done, that's it. You have the for each optimizer, you do a training loop of 500 epochs or 5,000 epochs, right? Sorry, 1,000 epochs. So that's it. So when you run this, you now see, of course, I have subplots. I have plots here going that basically plots two things. It plots the it plots three things for each optimizer. It plots the loss history, it plots the decision boundary, and then it plots the actual versus predicted values for 1,000 epochs. Interestingly, you see a lot of different characteristics here. So let's take a look at some of them. The first thing you notice is at the beginning we're using a stochastic gradient descent. You can see how the loss history drops. It's still slow at the top, right, and faster at the bottom. And then you can see the decision boundary here. And then of course it's actually able to get 100% accuracy because this is not a difficult problem for a neural network. For RMS prop, you can see RMS prop drops faster because RMS prop has a kind of built-in, remember RMS prop is the one that has pay parameter learning rate effectively. That RMS that you are doing, the root mean square um, of the gradient, right? That root mean square. That's when you take the square of the gradient and then you sum it up to previous squares of the gradient and maintain that moving average that we talked about that looks into the past. That actually helps. So at this point, when gradients are higher rather, at the beginning, we are seeing that the loss is dropping faster. But at this point where the gradients begin to reduce, the loss slows down. So this is a much better curve, right? For compared to the SGD, where at this point it is still slow. It is quite slow. it only speeds up here a little bit, right? But actually, it speeds up in the middle and then slows down at the end again. But the beginning is also quite slow. And this is typically the curve of SGT. It's always that. Um, yeah, I did not put metrics like accuracy and so on this. Maybe I should add those. So that's RMS prop. Now this is momentum. This is basically SGD with momentum. Again, you see momentum is what causes this huge drop here, like a cliff. This sudden drop. Because at this point the gradient is very high. But you see that at the point when it drops and the gradient reduces considerably because essentially the parameters have adjusted, you now see that at this point it flattens out. Okay. Nesterov is going to be similar to normal momentum because Nesterov is also a momentum factor that is added to SGD. So you can see it also drops similarly and then it flattens out. Adam is now a combination of RMS prop and momentum. So in a way, you see it kind of drops suddenly, but it is not as sudden as these other ones. So in a way, I guess that means a bit more stability. Adam with weight decay drops almost the same as regular Adam. So they will behave more or less alike, because both of them are the same. The only difference is that in the Adam with weight decay, the weight decay factor is taken out. Then this Adam with Nesterov momentum rather than the regular momentum. And you can see this also drops really fast. In fact, this drops the fastest. So you could say, okay, this gets you to your final loss much better. Then other grad also drops fast at the beginning and peters out. Other delta is more like a gradient descent. It starts off slow, but it drops at a linear basis, after an hour, and it never flattens out. Uh, then other max is almost like um Nestor of Adam, right? And then this is R prop. So you can see R prop is like a sudden cliff that just drops down and then it stays there. Then you have ASGD. ASGD is also similar to stochastic gradient descent. So it's the SGD in here in SGD is stochastic gradient descent. So that's it. And if you want to find the optimizer that has the lowest loss, I had this here that checked through all of the information and it gave R prop. So R prop ends up getting the lowest loss. You could actually check all of the loss values, so initial loss and final loss. If you take note, you see that they all start with the same initial loss because we are always resetting. Here, the final loss is 0.04618, but here the final loss is 0.000. Yeah, so this is very simple data. Um, what I will now do is I'm going to um, add some additional random data to the data set. So we're not just using that basic just 4 data points. 4 data points is too small for a neural network. It will basically overfit, right? So yeah, I think we did that last week. So I want to just pull that up from what we did last week. Okay, so we can use this. Let me just bring this in. So rather than just using 4 clean values, we are going to add random values. So we already have X here. Let's see where we have the X. So this is the original one, okay? But I'm going to replace this with um, a new X. So we'll just call it extreme. We'll use NumPy and VStack, and then we'll convert it later on to so so what we are doing is we take a random number. Um, this is the shape basically, right? So we'll take 100 rows. Maybe we could even take 1,000. Let me take 1,000. So 1,000 samples, right? Two columns, of course, so it maintains the two features. Then I'm going to modulate that a little bit because the random numbers. Um, 0.2 kind of allows you to modulate the range, right? And then you add that, you broadcast that to -1 and -1. So what this does is, of course, that um, since your random is ranging from 0 to 1, 0 to 1, when it is 0, right, plus or minus times a range. So the range is not going to be the full 0 to 1, right? It's going to be 0 to 0.2. So what that means is that this will extend, right? Um, 0, when it is 0, this will be -1, and when it is 0.2, this will be minus 0.8. So effectively, it is going to range around 0.2, but I'll increase this to 0.5, maybe even 0.6 to see how that extends. So, and then we just keep doing that for the remaining ones. So, so we extend it -1 and 1, which is the first one, then 1 and -1, and then 1 and 1. And that gives us the full range of noisy. This is now a noisy exclusive of, right? Um, but the so I can also say extreme equals touch tensor extreme. So I convert this into a tensor basically. Um, right. And that's it. So the difference now is that I have introduced a bit of more data points, 1,000 of each type instead of just one of each. So this is going to give us 4,000. And if we plot it here, you see that it's much more. It's much more, and there's a lot of noise. Now, I was doing color mapping here before, so it kind of ran out of data already with this color mapping. So what we could do is rather than using a color map, um, we're using okay, I'm surprised that the color maps is not differentiating. So there is a different way we can plot this. Rather than using a color map, I can just separate the two of them and plot them as separate. Yeah. Let's do this. Plot when y is equals to 0. Uh, when y is equals to 0, and when y equals to 0, the value is 1. So plot x when y equals to 0, and the first, basically the first feature, the first column against the second column, right? But here you plot only when y equals to 0. So you plot that one, so we can specify the color for that one. And we don't need to use a color map. And so in this case, I can just give it a label, and the label is, let's just say true, right? So that's the class is true. Um, then we'll do the same thing, except that this time we'll plot only when y is 1, as when the true value is true. The other one is when the actual value is true. Here is when the actual value is false, right? And okay, yeah, this should be false rather, while it should be true, and it would figure out the colors by itself because um normally uh matplotlib actually switches colors when it is printing. Okay, so we'll go back and try printing again, and this time we should get better um oh, okay, yeah, I forgot the size. I changed the size. Let's start again. I think I've missed something, so let me rerun this. Okay, okay, yeah, okay. So the problem is that I forgot to change the y. The y should match yeah, the y should match um I should stack the y's as well. This is just 4y values against 4000 x values. That is the cause of the problem. So I am again going to use NumPy to generate for y. We'll do an array basically. So what this means is that um, we'll have the first, because we are doing vertical stack, right? Would first do the first 1000 will be zeros. The next 1000 will be zeros. The next 1000 will be ones. The next 1000 will be ones, and the last 1000 will be zeros to match the x. Okay. Then we convert them to PyTorch tensors. So this should be Torch tensor Y train. Okay, so in case you're wondering what is happening here, think of this like vertical stacking of a number of um, a number of tensors. So this first line here, what this first line does is it first of all generates a random number set that has this shape. So it has 1,000 rows. Okay, that is, and then it has two columns, x1 and x2. So that's effectively what this thing is doing. And these are random numbers, so they can be 0 point whatever. They are random decimal numbers that range from 0 to 1. Okay. And there are 1,000 of them, basically. All the way down, there are 1,000 of them. So that's the number of rows, but two columns. Then when you multiply by 0 0.6, you are basically changing the range from 0 to 1, which is a typical range of random number, to 0 to 0 0.6. The range is now 0 to 0 0.6. So the highest value of these random numbers will be 0 0.6. Okay. Then you add that to another array that has -1, -1. So imagine just adding this to an array of -1, right? For what you add to x1 and -1. So what you end up getting, remember the random numbers are from 0 to 0 0.6. So when it is 0, this will be -1. And when it is 0 0.6, this will be minus 0 0.4. So the range of this will be -1 to -0 0.4. Okay. Here, same thing, right? -1, -0 0.4. And you have 1,000 of these because you are basically stacking the whole thing. So you end up with a random number that is in the range of -1 to -0 0.4. This is just to help plot the graph. To help plotting the graph. Then um, you can see this also does the same thing, except that now it is these numbers are less than 0, right? So ReLU will basically trim them up. They become zeros. These ones, one of them is 1. So if it is 1, the range is effectively going to be um 0. Sorry, it's going to be 1 to 1.6, right? For this one, while this will still be -1 to minus 0 0.4, and so on. So what you end up with is something that kind of rotates around that exclusive orange. Okay. And then the outputs match that. So for the first 1,000, we are generating zeros as the Y values. That's what this first term does. This is not an actual multiplication because this is not a NumPy array or a torch tensor. This is just a regular Python list. And when you take a regular Python list and multiply by a number, it is not 1,000 times 0 inside here. This is expanding 0 into an array that has length 1,000. That's what this is doing. Here, it is expanding this 1 into an array of length 1,000. And then this one is also expanding this 1 into an array of 1,000, another array of 1,000 that has zeros in it. So effectively, you are creating the Y equivalent Y values for these four sets of X values that you have created. So that's what's going on there, in case you're wondering what is all of that doing. Okay, so now this should give us a more a wider range of values, which I again want to print here. Right, so you can now see there's a lot of overlap here, which is really what I wanted to do deliberately. So this is not just a straightforward exclusive OR problem. At least this will be more difficult for a neural network to learn. I probably should have added some transparency in the chart so that yeah, but okay, let's just keep going. Okay, So we continue. So we have you know um 14 or 15 different optimizers here. Then we have the training loop. So um training loop will still plot the decision boundary. So at the end of the day, this is a more complicated problem with more data sets. So this will take a bit longer to run. The other one we just had 4 data sets. That's why they were able to do very well. Um, yeah. So let's now look at each of them. You see that some are doing better than others, and um, there's still a lot of overlap, right? This time around, you see how SGD is doing. It drops a bit faster, but look at the decision boundary. Okay. Um, this is RMS prop, drops faster. But the loss, final loss 0.21978. This one is 0.25281. So you can see RMS prop actually got to a better loss. The momentum gets to 0.22, which is interesting. It's not as good as the RMS prop. Then the Nestor also got to 0.22019. So basically, the two momentum approaches give us the same loss. This is Adam, 0.22336, right? It's even worse than ordinary momentum. And then Adam with weight decay 0.2315. And then Adam with Nesterov 0.2577. Adagra 0.22511. Um, Ada delta is 0.40714. So this is very poor. Okay, I even see a decision boundary is not very convincing, right? It's not very convincing. Then yeah, Adamax 0.21920. And then R prop. So R prop gives us 0.21. R prop still gives us 0.21874. But here you see that R prop is, let's see, we had very good values from RMS prop. And RMS prop gave us 0.21978. That which is about the same thing as what R prop is giving us. 0.2187. Okay, R prop is giving us 0.21874. And then HGT. So if you look at this and if you run this one again, at the end of the day, still R prop that gives us the best loss. So it's interesting that let me change this to not overlap, right? So the overlap is causing a lot of problems. So let me change this to not overlap. Basically, we'll just go to 0.5. Then let me run it again. So here you will probably see much better losses. Okay, this is the on trade model. You can see it's giving us a linear decision boundary. So it hasn't been trained yet. But after some training, you can already see that some of these surprised that I am getting, yeah, some of these are not giving me very good decision boundaries. Nestor also is giving me a better decision boundary. HGD is giving me a good decision boundary. So that's just to show you hands-on on um, optimization with PyTorch. Okay, let's talk a little bit about regularization. So sometimes you do training, right? And you find that you're having problems. Your model, something goes wrong. Most of the time, what goes wrong with models when you're training is either underfitting or overfitting. We talked about bias variance, last time. That's really what this is. Okay. Um, in most cases, the issue may be that you have um, you have a model that is too complicated, or sorry, too complex, too big for the data, or that will give you overfitting, right? In fact, for neural networks, that's mostly what happens. And that happens most of the time, mainly because neural networks by nature actually uh, have a lot of parameters. They are very large models with a lot of parameters. So it's always going to be very, very highly likely that you will overfit if you are not careful, right? So in order to kind of minimize the um, probability of that happening, we will talk about um, different ways to handle that, right? Um, Overfitting is normal, it's not a bug. You said overfitting just means that your model is able to track all the nuances in your data. Okay. Um, Regularization comes as a technique that you would use to minimize overfitting, reduce it significantly, and improve generalization. Of course, overfitting and generalization are opposite. If you're overfitting, that means your model is not generalizing. Overfitting simply means your model is doing very well on the training data you gave to it to learn from. But on the validation data, it's doing poorly. So obviously it's not generalizing. Generalization means it the knowledge it gains from the training data, it's able to apply it in data out of band that it never saw, and still will be able to get a pretty high accuracy. So then you also need to be able to read loss curves, which we've been plotting loss curves all this while, but we've been plotting just a single loss curve, right? Typically, you would want to plot both the training losses and the validation losses in the same curve so that you can compare. That's when you will know whether you are overfitting, whether you are in overfitting high variance mode, or underfitting in high bias mode. Okay. And then with that, you can learn how to interpret those loss curves and debug your training, right? Instead of doing guesswork. So some of the questions that will be answered here would be why your model is performing well on training data but poorly on validation data. Should you stop training or continue? And how do we know if the model is too simple or too complex? And what other parameters, knobs, basically, what are the parameters that can be adjusted or tweaked in order to minimize that divergence, right? Is when the model basically the validation loss basically goes away. Okay. So we've already talked about overfitting and underfitting, but I'm just going to do a quick recap. So overfitting occurs when a model learns the noise in the data, quirks and specific examples of data. So learning patterns that can generalize. So that even on data it has not seen before, it should still be able to give pretty high accuracy, right, by prediction. But when it starts looking at the patterns, noise rather in the data and breaks, it's effectively trying to memorize that data, and it will, and try to get you know high accuracy on training data, but it will be useless. And most times when you train a model on training data, you're not training it so that it will predict the training data because you already have the training data. You're training it so it will make predictions on new data it hasn't seen. Okay. So typically what causes overfitting is when your model has too many parameters, when the data set is too small or too clean. Too clean is very key. Too clean means, like I just did now with the exclusive OR problem. Too clean was the initial case where we had just exactly 4 data points, right? And that was easy. The model would actually overfit on that after some time, even though that is not the the two-layer perceptron we had there, that one with a single hidden layer is not complex enough to actually overfit on exclusive OR. It will still give you a decision boundary that typically works. But if you had a really more complex neural network, then it will easily overfit. So that's the second reason. If your data set is too small, the data is too clean, there's no noise in the data, That's the interesting thing. Neural networks learn very well from data that has a lot of noise. Okay. And as a matter of fact, sometimes it is you introduce deliberate noise in the data that you want to train a model with so that it learns what is noise and separates it away from what is the signal, what is the actual pattern that's trying to learn. So that is called different names for it. There's a terminology called Dirichlet noise, and there's another terminology called temperature, right? Those are just two of the different ways of introducing some noisiness. Another way is we'll talk about that when we're talking about regularization. There is dropout and so on. So if training continues for too long, there will also be overfitting, especially if the model is too complex. And there are no constraints on the weight growth, so the weight continue to grow. So typically, the key symptoms of overfitting is that as the training loss is dropping steadily, you now have validation loss beginning to go up or stagnating. Validation loss flattens and training loss keeps dropping. Or in some cases, when it's even worse, the validation loss starts going up, right? But validation accuracy will peak early and then start dropping, degrading. We saw some of those when we looked at some of the curves earlier on. Overfitting doesn't mean that um, you did not train your model well. It just means that the model has a lot of capacity and it is unused. And your data is probably not enough to use the full capacity of the model. But you still want to use that model to train on that data. Okay. So um so um Yeah, so this chart show you differences, right? Underfitting, you always have underfitting. You have a lot of data that is non-linearly separable, for example, and you go and use a linear model basically to try to fit into that kind of data or learn that kind of data. And that's what's being shown here. This is a linear model, so it can only draw a straight line as a decision boundary. But you can see that you cannot really make a perfect separation or classification, without using a nonlinear decision boundary, right? So for this one, for example, the true decision boundary has to be something like this. These other two are kind of outliers, noise, so you're not going to try to go into those, right? So this is underfitting, right? Here, this is appropriate fitting. So this is exactly doing what it should do. It's cleanly separating these two. Even though we have two data points here that should be on this other side, but they are noisy. This is overfitting. So here you can see that this model has actually learned to separate, this one is actually on this side of the line, this one's on this side of the line. So, and then these ones are on this side of the line. So it has successfully separated every single point here, you know, into their classes, using this really complex, um, curved Bezier decision boundary. But the truth of the matter is that this is not very correct because this is now overfitting. It's learning the noise. These two are probably outliers. They're probably noise in the data, right? And so a proper learning is not supposed to try to adjust itself, or its decision boundary to accommodate these two. But even if they are not noise, they are outliers. So it also means, yeah, that's why your loss will never be zero. Because in real data, in real life, there will always be data points or samples that you cannot adjust and make them fit into the other side or into the right side of the decision boundary. But here you have a loss of zero. But if you now take a new data point, here you can predict that, you could even predict that this decision boundary will extend this way, maybe extend quadratically, right? Or maybe extend into an ellipse or something. So if I were to pick a data set here, you should be able to classify it properly, or here. But the problem with fitting to this kind of other one, right, is this is a Bezier, so it's not going to remain straight at these edges. It will also keep twisting and turning this way, right? Because the parameters have to adjust in such a way to do that. So if you have this, you may actually have a situation where if I had this one here, it will misclassify it. So you find that overfitting always tends to result in um, misclassification when the data is new unseen data, right? Um, you could have this here, right? A bunch of these lighter green ones, right? Going this way. And maybe it is an elliptical decision line, but this is now misclassifying it because of how we had to adjust. So that's kind of what overfitting means. Um, then we also have underfitting, right? Underfitting is when you have high bias. High bias is when the model is too simple and it cannot fit the data. So again, this is just the same thing. This is underfitting here, where you have a simple linear model, but the data can only be predicted. This is not a regression problem. It can only be predicted by a regression line that is curved. So a linear model would not do a good job on this. A quadratic model could do, or this looks more like a circle. Uh, Now this is overfitting because it's basically following every single point. But again, if you want to extend the prediction into um, unknown data, this results in you know miss prediction of a lot of different data points. So for high bias, it happens when your model is too simple. So if you're using linear model, like I said, for nonlinear data, if the layers in your neuron are too few, right? The fewer your layers of your neural network are, the closer it is to a linear model, because a single layer is actually exactly a linear model. Two layers is not a linear model. It's a nonlinear, but it's not a very complex nonlinear. I cannot trace out this kind of curve. Two layers would more likely trace out maybe second order, um, you know, um, polynomials, right? So for the more the layers, the more complex the relationships. So typically symptoms of underfitting is high training loss, right? And high validation loss. Both losses are high, which would be interesting, right? But that's really what happens. High training loss, high validation loss. Now, typically, if you were overfitting, you would at least have low training loss, but high validation loss. So the more you train, the less improvement. There's no improvement when you train. Unlike with overfitting, if you train, the training loss improves, gets lower and lower, right? But the validation loss stays the same. So that's high bias underfitting. High variance is overfitting, which is what we just talked about. In this case, model is too flexible and all of that. It learns noise instead of the patterns and the structure. Training loss is always very low, while validation loss is very high. And there's a large gap if you're plotting the graphs. So the question now is, what is regularization? Why do we even need regularization? Because neural networks are very high parameter models, right? If you look at what we just talked about now of variance or overfitting, right? You see that whenever your models are very complex, far more complex than the data that is available, they will tend to overfit, right? And neural networks, by the nature and design, is very easy to pull them together, multiple layers. So there's always a high tendency to overfit because the models are very flexible. So the only way you can counter it, right, is what we call regularization. Regularization is a method that limits the model capacity. It kind of deliberately limits the model capacity, therefore bringing it back into the region of the bias, the region of underfitting. But then it is to counter overfitting, so it kind of balances it out, right? It adds constraints that discourage overly complex solutions, right? Or overly complex decision boundaries, right? Regularization basically means adding, or the way it's implemented is you add a penalty to the cost function that grows with parameters. That's what regularization is. So um, the cost function is calculated, then you add the penalty to that cost function. And the penalty is a function of the number of parameters in a model. So a model that has more parameters will suffer a higher penalty. That is how it kind of counters um, the overfitting, which larger models would normally do. But larger models will have more parameters. Simpler models will have less parameters, so the penalty will be less. So the idea is simply that simpler models will generalize data. Large weights often in fragile solutions. So the penalty is to reduce the capacity, basically prevent if the model is too big, then the cost is higher. And that forces the uh, model basically to um, learn non-complex decision boundaries, simple decision boundaries. Simple, smooth decision boundaries are more robust to noise. Like, like I mentioned. You have decision boundaries that are trying to fit everything, then they tend to overshoot and go to parts in the unknown space where there is no training data. They tend to go all over the place. So instead of calculating a minimum value, minimum loss, right? You calculate minimum loss plus the penalty. So we'll look at what this penalty is. The penalty that you put in is what determines the type of regularization. We have a bunch of others. Well, there's the one that is based on penalties, and there's the one that is based on other methods, which still kind of act as penalties, but not from margins. So the first is the parameter-based penalties, where you add some additional parameter. The first one is the L2 weight decay. Remember, we talked about Adam with weight decay. So that weight decay is a form of regularization. And then we have L1, which is L1 penalty, L1 regularization. So this is loss function with L1 regularization. If we look at loss function L1 regularization, all we did here is this is a regular cost function, right? Which is y minus y hat, right? For each value of I, it is summed, okay, right? It is summed and then the average is taken, even though this should include a square. This should actually include the square because this is root if you are using RMSE, mean square error, for example, and there should be a square here, so take note of that. Because just doing a loss function without using an absolute value will not give us a proper loss. So this should have a square for root mean square, or it should have an absolute for um, mean absolute error. For mean square error, you have a square. Mean absolute error, you should have the absolute value. So, but yeah, but this is just take this as the standard, RMS. Let's just take this as our standard RMS, mean square error, right? Now, in the standard mean square error, right? Let me just help with the visuals here. So this is squared. In the standard mean square error, right? You would then add a penalty to it, right? And the penalty that you are adding is basically sum of the weights times a factor called lambda. This factor is the regularization factor, right? So what this lambda does is to regulate or to control, the amount of regularization that you apply. So because we are just adding the sum of, the weights, this is actually the absolute value of the weights. Because some weights may be negative, and some weights may be positive. So again, we want to add them all up. Because if the number of weights or parameters are high, but you have equal number of negative and equal number of positive, what you are ending up doing is neutralizing. So same thing when we're calculating cost, error, and so on. So here, this time around, we are summing the weights, not um, the error. So the more the weights, right, the higher this value, this sum will be. If you have only 10 parameters, okay, if you have only 10 parameters, it will be much less than if you had a million parameters. this sum. So that means the larger one would have a higher penalty, basically. And of course, like we say, use this lambda to tweak or adjust how much of that penalty is applied to the cost function. And that's it. So when you have regularization, that's L1. We'll go into more detail on this anyway. So you have the types of ones you have is weight decay, L2, then sparsity. So L2 results in reduction in weights, basically. That's weight decay. Then L1 results in sparsity, most zeros. The difference is one of them is a square error, one of them is absolute. It's not a square error, it's absolute value. So we'll look at that. Then we have stochastic regularization, where you are not using some mathematics or adding some penalty, but you are actually adjusting um, parameters in the model itself. So dropout is one, noise injection is second one. Then you have database regularization. Here, data augmentation and label smoothing, right? These ones, we'll talk about them again. Uh, and then we have training time regularization. So the data itself can be adjusted to, enforce some kind of regularity. And the training time as well can be adjusted. So we'll look at all of those. Okay. So one of the things you see is that regularization forces a model to stay in this region that is pretty good, rather than going out into the overfitting region side or the underfitting region this side. So let's start with the first one, L2 regularization, which is the one that is really used a lot these days. Okay. Um, so what you just do is you update the loss function by adding this lambda theta, right? Lambda theta squared. Okay. So this is basically sum. This is a sum of all the parameters. Okay. Um, so the lambda controls the strength of the polarization, while theta are the model parameters. It's called ridge regularization because it creates a ridge-like surface in the cost function that helps optimize unstable large coefficient models. Okay. This is ridge regression. Sorry, ridge regularity. The effect of this is that it penalizes large weights because it's a square function. So remember, square always increases, anything that is square always increases the effects of large values, right? Then it encourages small distributed weights. It encourages small distributed weights. So that's just the opposite of penalizing large weights. Produces smoother decision boundaries. Yeah, because it reduces the capacity and makes them more of non-linear, but more of a polynomial kind of, right? Why it works is that it prevents any single feature from dominating. Prevents any single feature from dominating. It improves numerical stability because its value is high, right? You want a low loss, so you always try to um adjust. The optimizer will always try to adjust for lower um parameter values, rather than trying to go high, because if the parameter values are high, the regularization penalty will also be high. Remember, the penalty is a sum of the weights, the absolute value of the weights. So the penalty can be high if the number of weights is high, right? Or the number of parameters is high. But the penalty can also be high if the value of each parameter is high, the high side. So you find that um, it always tends to uh, optimize for low parameter values. So that's L2. L2 is square. You take a square and you are going to sum all of them. So this is kind of sum. It's strongly tied to better generalization. So in practice, L2 regularization is like the default choice in deep learning, right? And in optimizers in PyTorch, you specify it as a weight decay. Specify it as a weight decay, and you can specify the lambda value that you want to use. for that weight to get as one of the hyperparameters. Okay, so the second one is the L1 regularization, which is the lasso um, regularization. So the lasso regularization uses the L1 norm, right? Here is the L2 norm. You can see, so this is square, right? But here's the L1 norm, which is just the absolute value without a square. So this is kind of like similar to mean square error and mean absolute error. Mean square error is using a square of the errors, right? While mean absolute error is using the absolute value of the errors. Same thing here, right? You are using a loss function. Here you are using the absolute value of the parameters. So whether it's negative value of parameter or positive, they all come out positive and they are all added together simply, right? And then you still apply the regression factor or constant. Okay. And it's the same thing, right? But this one is called the lasso. And lasso actually is an acronym that means the least absolute shrinkage and selection operator, right? It uses the absolute values of the coefficients to penalize the large weights. The absolute value of the weights themselves, the parameters themselves penalize, right? It doesn't use a square, or like L2. L2 uses a square. And that's why it's called L2, because it's second order, while L1 is first order. Now, one of the problems with using lasso is that it tends to push a lot of weights exactly to zero, because you'll find that that flexibility is not there. Um, the without squaring, right? The parameters can actually regularization values can actually be pretty high. But with squaring, remember if you square a number that's less than one, you get a smaller number. You don't get a bigger number. It's only if you square a number that is bigger than one or larger than one that you get a bigger number that keeps growing, right? And may result in numerical instability. But if you square a number that is less than one, it begins to shrink. It keeps shrinking until it gets to zero anyway. But yeah, the amount of shrinking, the amount. So if you are using square here, the actual amount of regularization is going to be less, right? For the L2, but it's going to be more for the L1. And the only way to compensate is the actual parameter values dropping to zero. That's the only way you could reduce. So it ends up producing what we call sparse models. A sparse model is a model where there's a lot of zeros in the parameter matrix, right? A sparse matrix is a matrix that has a lot of zeros in it. So L1 is useful because it has implicit feature selection, interpretability, and compression. And you typically use L1 for more simple regression models like linear and logistic regressions. You won't see them being used a lot in neural networks or deep neural networks. Because of that, this property of producing sparse models, models with a lot of zeros. You don't want your neural network parameters, most of them to be zero because you're effectively switching off a lot of the capacity of that. So those are the two that are based on penalty. Then we have dropout. Dropout is basically saying when you are training a model, drop some neurons with a probability P. So that means when if I had a fully connected network, maybe let me see if I can demonstrate what dropout does. So let's assume I have a simple neural network, like has these four neurons, right, in the hidden layer. And then remember, this is fully connected. So I also will have a bunch of inputs are connected to it, right? So let's say I have two inputs just to indicate. So the first input connects this way, and the next input also connects this way. So dropout basically means I can take out some of these connections, right? Remove them. That's why it's called dropout. You drop this neuron or you drop this connection. Okay. And when you drop this neuron or this connection, then the model will learn how to predict the same output, right? Without using those neurons that have been dropped out. So let me complete this just to show you. So that's the hidden layer, right? You have input, you have the hidden layer, and you have this output layer. And you have a two neuron output layer. Now, of course, you have to join this, right? So each of these feeding the two, each of them feeding two. Okay, so yeah, so this is our simple neural network two outputs. Now, normally, if you're training the model, you train with all of these neurons intact. But what dropout does is that every cycle of training, it drops out one neuron, or it drops out neurons, any number of neurons with a probability of p. So you use a probability function to determine whether to drop out or not. So for example, I could drop out this neuron. If I drop out this neuron, then it means that these weights here are basically useless. They're not transferring any information, right? Um, so the, uh, the information is now circulated through these other three um, neurons. So what dropout does is it actually introduce some kind of randomness as well, but it is architecture-based randomness as opposed to data-based randomness or mathematical randomness, which are two different things. The next cycle, we could decide to remove another weight, another neuron rather, right? And so on and so forth. The next cycle, we can decide to remove another neuron. So at the end of the day, you find that each of these connections learns to become robust and learns to be able to predict the same outcome just with a fewer number of connections. There's a kind of redundancy. Effectively, dropout means you are creating a redundant pathway, multiple redundant pathways, for the feed forward to get to the same prediction. Effectively, that's what dropout is. So when you are doing normal um when you are training, during training, when you are training, what happens is that the neurons that have been picked will drop out based on this probability. Those neurons will not forward any information. They'll just send zero activation as if they did not exist, right? In fact, they will not send anything because zero is still a value, right, in the neural network. That's what happens. Of course, dropout doesn't apply when you are doing inference. When inference is being done, all of those neurons will be brought back in. So they will still contribute to the inference, but your inference will be more robust. But effectively, what has happened is that the network has learned different ways of looking at the same thing with different amounts of noise. So it's able to actually pull out just what really matters. Okay. So the effect of dropout is with this, neurons don't really rely on each other. Neurons effectively learn from data instead of relying on the other neuron to kind of handle that prediction. It forces redundant representations, so multiple representations of the same knowledge. That makes it much more robust, like we have seen. Then, yeah, so the way you can think of it is that each batch is training a different subnet, different subnetwork for a different pathway. So we can take this as training an ensemble and averaging. Remember what we were saying when we talked about random forests, right? Or XGBoost, where we said, okay, you have essentially ensembling multiple decision trees, and each of them is trained on a different subset of data. So they learn differently, right? And then you take the average. That's kind of what dropout does as well. So it's effectively like saying each of them learns slightly different things, right? Or different subnetworks that learn the same thing rather. And so when you put all of them together, they will tend to be average and they will tend to be more robust. So the typical rates that you would choose when you are doing dropout is 0.3 to 0.5. This is a value that represents how much of the neural networks or neurons rather in each layer are dropped right at each cycle of the training. For convolutional layers, again 0.1 to 0.3. So that's dropout. The next one is okay. So the other thing I want to mention before I move on is dropout in the training phase, right? This is again another graphic presentation of it. This is a fully connected network, right? With three layers and one output, three hidden layers and one output layer. So when you apply dropout, you now see that some of these, the ones in red, essentially are switched off. They don't send any signal. So the training is the weights, the only weights that are being updated are the ones that are connected to the green. Okay. So this happens when um you are training, right? So the neurons are randomly disabled. The outputs have to be scaled because the gradients will differ. Remember, gradient has to do with the it actually has to do with the number of parameters. So when you switch off some neurons, the number of parameters actually reduces. Okay, but outputs are scaled implicitly. Then when you're doing inference, you switch back all the neurons. So dropout does not apply when you're doing inference. When you're doing when you're just using it for inference, not for training. Okay. But in that case, activation will scale to match the training expectation. So there is no noise at inference, only robustness is learned from the noise. So effectively, Dropper is injecting noise during training. But like I said, the noise is coming not from the data, right? Or from some mathematical application, but from the architecture itself. The architecture is being altered in small ways that introduce a bit of noise. So that encourages stable predictions and reduces reliance fragile path. Because if not, if you're relying on a single path, let's assume that um, the model was trained without dropout and it ends up relying on just a single pathway for a specific prediction. Then if that pathway is compromised, one way or the other, then the prediction may fail. So that um, affects the reliability. So that's dropout. So there are a bunch of others which we um, when I was talking about all of the different ways that regularization is applied, right? The dropout is one, then the noise injection, which even though I will not talk about it, but let me just give a summary on that. Noise injection is when you inject noise into the data. So um, you can vary the data a little bit, right? Inject some random noise, either as part of synthesized data, right? What we call temperature or Dirichlet noise, or the data itself is noisy. Okay. But if the data is not noisy and it's very clean, you can actually introduce some noise into the data as part of training. So you have additional what we call augmented data. Remember, we talked about data augmentation as one of the things you can do in the data reprocessing pipeline, where you could, I will talk more about data augmentation. So that's one of the things you can do. Then training as a way of you know regularization. It's early stopping. Early stopping, we've talked about that already. So it just basically plots your training error, right? And then plots your validation error. Okay. And then whenever you see that your model is basically beginning to drift away, the validation is beginning to drift away, you can see here validation begins to rise. While training error continues to drop, then you are overfitting. From this point, right, you're already overfitting. And so you should stop training immediately because there's no way your model is not going to get better, on real world data. So that's early stopping. Is you use validation performance as a metric. Once it stops improving, before overfitting begins to dominate, you stop training. So for this, it requires that you have to monitor both validation and training loss and compare. And then secondly, you have to keep saving the best model checkpoint because sometimes you might diverge or overfit so much that it's too bad. The current model is so bad, you may not want to use it. So typically you go back to the model that was saved as the best. Okay. And then you have what we call a patience threshold. The patience is the extra number of cycles of training epochs that you go once this validation begins to drift away, mainly just to be sure that it's not noise. It's not just a temporary spike or a temporary thing that will go back, right? Because sometimes you can have a situation where maybe some especially if you're using batch mini batch, gradient descent, or you are training with whatever mini batch is, a particular batch that might be really difficult for the model to predict, right? Even though the validation should still be the same, right? It shouldn't be different batches. But yeah, but there might be a situation where maybe the model was trained and it went a bit away, so it's not really predicting well. Its validation error goes up, but it comes back down after some more training. So you want to be sure that it is actually overfitting before you stop. So that's what the patience does. You count through it. So patience can be a value that depends on the number of epochs that you are currently training. So early stopping is regularization through time. And it's very powerful because you don't need to do architectural changes like the dropout, right? And there's a minimal compute overhead, unlike the L1 and L2, where you have to do a lot of computation and you work with any optimizer. Okay. So in all of this, what you will have seen and noticed is that your loss curve is very, very important. You can see the loss curve is the most important tool. You need to be able to read your loss curve to know what to do. So typically, what you plot in your loss curve is the training loss versus epochs and validation loss versus epoch, which is what this is, right? I use different colors so I can decipher which is which. So essentially, um, the blue is the training loss, right? And the orange here is the validation loss. These are actually real losses that we got from real training stuff. So what they will actually reveal to you and how you can interpret it is very, very critical. Okay. So for example, one, your model capacity. Is your model too small? Is your model too complex? Of course, it becomes clear if your model is too small, then you're underfitting. And you can see that both losses are high. This is very important for you to these guidelines are very key for you to be able to interpret. If your model capacity, if you're having on underfit, right, which you can tell by checking and you see that both losses are high, no matter how much you train the model, then it means your model capacity is low. And the solution is for you to increase the capacity or change the model architecture, the model type, right? You also have flat curves. The model is too weak or learning rate is too low. If on the other hand, if you are overfitting, right, then like we said, training loss will drop continuously while validation loss will bottom out and then begin to rise if you still continue training, right? And the gap continues to increase over time. That's a terrible overfitting. Sometimes it flattens, it doesn't increase, but overfitting is something to watch out for. And if you're overfitting, that means your model is too complex, and the solution in that case would be to either reduce the model size or apply regularization. Regularization will counter overfitting. Then other things you can see is optimization failures, right? Learning rate problems. Again, learning rate also affects how well your model converges, especially at the tail end of your training. It's always a good idea to ask yourself, should I lower the learning rate? Because that is where the loss landscape becomes, very small. You start having really small, tiny um, global minima, and you actually need to use smaller learning rates so that your model can find its way into those. Learning rate problems, what I just said, overfitting versus underfitting. So when you have healthy training, you see that both losses will increase, and there's a stable small gap between the training and the validation loss. And you see that validation loss tends to track the training loss. It follows it. The validation loss will be a bit higher, even though here I'm seeing it as the validation loss is lower. But then sometimes you actually have where the validation loss is lower. If that happens, it is mainly because the training data is much more than the validation data. Remember, the loss is the sum of the errors across all the data points. So if you have more data points, your loss calculation or your cost function calculation the value will be higher than if you have less, even though it is mean, nevertheless, right? It is a mean, it is a square mean, right? Um, but more data tends to also have more loss. So there are times when you see that your validation, if your validation loss is lower, It should be higher than your training loss. But if it is lower, it means that your training data is more difficult for the model to learn. Maybe because it is far more in number, so it has more variety of position of samples of um, the expected value or the not expected value, the true value, right? It has more variance of the relationships. So you find that yeah, the training loss will always be higher. So, but that is not to say that I cannot really interpret that any more than saying, okay, the validation data is easier for the model to predict. In that case, what I would typically do is change my validation data. Not in the middle of that training though, because if you change in the middle of that training, you've changed the metric you're using to gauge how well your model is doing. But the next time you want to do another round of training, especially on the same kind of data, right? See if you can find data that is more difficult. So these are examples of loss curves. In this one, you see that train is lower than test. So this is typically like a good one. Even though you notice that the train is dropping, forget the noise, right? This noise that is going up and down. This noise is because we're using mini batches, right? So at each mini batch that you're training, you see that the model is actually learning more of that specific mini batch, right? So when you calculate the losses on validation data, it tends to jump around, especially yeah, test data here. But if you look at the more the longer you know, the longer term or averaged out trend, you see that the training is dropping and the test of validation is also dropping. But at this point, you see it begins to grow. So this is still some kind of overfitting, but it's not bad because the test is still dropping as well. The test is still dropping as well. This is another example of that one, right? The test is still dropping, right? The training is dropping much more. But you see that at this point, it had already started overfitting. Okay. But if it were me, I would still continue training in this case because the validation loss is dropping. But by the time you are here, if you were to just smoothen out these spikes, you see that at this point, it's flattening out. It's flattening out. Even though it does look like a training, it's also flattening out. So here you can see that your model is kind of overfitting, but it's not that bad. Okay, now this is another one. For this one, you can see that the train is much higher than the test. If you see this kind of thing, I think you need to check uh, your code. There might be an error because your test or validation should not be this low compared to the train, especially at the beginning. I've actually seen this happen, right? And it just goes down and then it flattens out. But this could also mean that your test data is too simple for the model. It's not challenging for the model to predict at all. So in this case, I would say I'll try to get more complex or maybe increase the test train ratio a little bit so that the test will get a slightly more data points or samples that you will use. So this is an interesting one, right? Where the training is not as good as the test. Now, this one is just crazy, right? This is basically the worst kind of overfitting. I'm assuming the red is the training, which keeps going down, but this flips. But you can see that this is like almost a mirror image of this. So what this would mean for me is that there is a sign flipping somewhere. There is a bug in the code, and maybe the sign is being flipped. And it's most likely is a sign of this blue one, maybe the test or training loss. So you would have to go and check how you are calculating those values. Yeah, so this is a summary of everything we have talked about. We started off this whole you know conversation with the loss surface. The loss surface. Now we'll round it off with the loss surface as well. So this is how you can interpret it. If your loss surface has flat minima, right, it means that small parameter changes will result in small loss change. So this will result in better generalization and more robust to noise, right? If you look at the loss surface of your parameters. But if the loss surface of your parameters have sharp minima, that means any small change in parameters, in inputs, in whatever, any small perturbation will result in a large um, change in the output. So this tends to overfit. Okay. Then the stochastic gradient descent also has a bias, and the bias of the SGD is that it tends to push optimization towards flatter minima. If you have a loss surface that is made up of flat areas as well as very sharp spiky areas with deep local minima and very tall high maxima, right? Um, it will tend to push optimization towards flatter minima, which is more stable and more robust. So that's why in some kind of problems, SGD will do better than Adam as an optimizer rather. Because Adam tends to push your model towards sharper, parts of the loss landscape, right? Um, so generalization is really about where you land, not how you land or not how low, right? Not just how low. There can be local minima that are very sharp, right? So and that's where Adam tends to go. Small changes, small perturbations, small few outliers, and so on, and it will not be able to generalize well. But SGD does better. Um, so if your validation loss begins to degrade, here are a few things you can do, which we have already talked about. You can increase regularization if you already had. If you did not have regularization in your loss function, then add some regularization. And remember, the adding of regularization is basically adding a lambda factor times the sum of either the square of the parameters or the absolute value of the parameters. That's just what regularization is. If you square the parameters before you sum, that's L2 regularization. If you just take an absolute value of the parameters before you sum, that is L1 regularization. Reduce your model depth or width, right? If you are overfitting, because model depth is a factor, it increases the capacity and complexity of your model. Width, same thing. Collect more data. So sometimes it may not be the model, it's just that you didn't give enough data, right? Because if you don't have enough data and you're training a model, that model will not perform well in the real world. So collect more data. Sometimes, even if the data is kind of just slightly different, maybe augment the existing data with a little bit of noise and so on, which is, this. Add noise, add different other transformation of the same data. Okay. Lower the learning rate. Yeah, that's another thing. You might be climbing up, um, you know, a hill in the loss landscape, and then apply early stopping if nothing else works. Okay. But the key thing is change one thing at a time and measure. Training models, if you want to really become very good at training models, one thing you need to understand is what should I adjust in this particular session? What should I adjust? How do I monitor the effect of my adjustment, right? Measure. And we already talked about the measurement matrix, right? Accuracy, recall, precision, F1, right? Mean square error, mean absolute error, root mean square error, all of that. Okay. Change one thing at a time, then measure. Change one thing at a time, then measure. Don't guess. So when you want to debug your training, maybe it's not converging or something. Some of the key questions you want to ask. One, is the training loss decreasing at all? If training loss is not decreasing, then you are you are underfitting. You have a model that is not good enough for the data, right? But so that's the first question. Is validation loss diverging, right? If training loss is decreasing and validation loss is diverging, then you have overfit and you have a model that's too complex, right? So, or insufficient data. So what you have to look at doing is all of the things we said, regularization, add more data, data augmentation, introduce noise, um, dropout, and all of that, early stopping and all of that. Are gradients stable? Are the weights exploding or dying? Exploding weights means the weights and the loss are increasing at an exponential rate. Dying means the weights and the loss are also decreasing. For neural networks, vanishing gradients is a real thing. And we're going to see it very soon. So the tools that you would use, the loss curves, like we've seen, gradient norm tracking. So there's a particular parameter called gradient norm, which you can calculate. Um, PyTorch actually gives you for free, so you don't even need to calculate it. You just get the gradient norm. You can plot it in the same graph, right? Typically, most times, if in those days of TensorFlow, you use something called TensorBoard. But the good thing is that PyTorch has an integration with TensorBoard, even though I think TensorBoard has been so useful that even now that TensorFlow is not really being developed, TensorBoard has been extracted and it's kind of a library on its own, which you can use. It's far better than Matplotlib because it allows you to actually interact with the curves. You can zoom in, zoom out. You can, um, you can you can hide or show some of the curves in the chart and so on. So it has a lot of capability. I think when we meet to do a bit of the training, I'll see how we can use TensorBoard or any other available chart tools. So weight histograms is also available in TensorBoard. It allows you to see the distribution of your weights, right? That helps you to really see it. Typically, the distribution of your weight should be kind of stable, not where you have some weights are so large and other weights are so small. They should be kind of evenly distributed, even though they will not be the same in value, but they would be evenly distributed. Then you can check your learning rate logs as well to see how learning rates have been changing, especially if you are using one of those adaptive learning rate optimizers like the RMS prop, like the Adam and so on. So when you're training your models, debug them. They are not black boxes, even though we call them black boxes, but as a machine learning engineer, you do have a bit of knowledge of what is going on, and you can actually, um, you know, um, you can actually do something about it, right? You can think about, you can adjust things, you can tweak things, and you would see the effect if you monitor them properly. So the key takeaway is overfitting will happen if your models are large and complex, like the deep neural networks, which we'll be looking at from next week. Regularization controls capacity, not performance, right? Loss curves are the most important training signal. So while training, plot as many things as possible on the loss curve. All this while we've just been plotting training loss or validation loss. But now you know you need to plot both of them. And then other things you could plot, including gradient norm, right? And then other things, not necessarily on the same plots anyway, but then you could even plot gradient norm on the same graph. You can plot a histogram of parameters and all of that. So good training is driven by your ability to diagnose issues and use your knowledge and these correlations that we have mentioned to know what to adjust. Which hyperparameter should you tweak? Is it the learning rate, right? Is it the betas, right? Is it regularization? and so on and so forth. So that is it. Um, I'll just share this with you because this maybe I'll just share this and you can go and look at it, but I'm going to walk through it so that you understand. So this is kind of um, a notebook where you are training the same model, but you are using two different optimizers, right? You are using Adam, uh, and you are using stochastic gradient descent, okay? And then you are comparing different aspects of regularization to see how it affects the training. So we trained with no regularization. We train with only L2 regularization. We train with only L1 regularization. We train with dropouts. And then we train only with early stopping. Okay. And then during each training run, of course, we plot the loss cause and interpret. So let's see how that looks like. So yeah, so the first thing that we did was just we find a data set that would overfit. So deliberately looked for a data set that has very small number of samples, right? With nonlinear targets, with moderate noise, a bit of noise in it. And then we design a model that has a very large capacity. So what we did just for simulation, what I did here was a one-dimensional sine wave that is noisy. Okay. The true function is a sine wave. We want the model to learn to predict the sine wave, not the noise around the sine wave, right? The noise would tend to make the model want to memorize every single data point and therefore result in overfitting. Okay, and it's easy to visualize. So let's run it. So if you look at this, yeah, we start up with all the inputs, and then this section generates a noisy data set. There are 30 training samples. Okay. That's what we start off with. And then we just generate it in a linear space. So the X is taken from a linear space, right? Of that 30 from -3 to +3. And then the Y is calculated simply by applying the sine function, right, to the X. But in addition to that, we add a little bit of random values, right? That are in the range of 0 to 0.3. Okay. Then, so that gives us the Y in addition to the X. And then we do the same thing to generate the validation data. The only difference is that the validation data, we don't add any noise, right? Because we want to see how well it does on non-noisy data, whether it will overfit on this noisy data and fail to predict this. And then we have a function here that does visualization. So you can see it has already visualized it. So this is the standard um, true value. Okay. While these red dots are the noisy generated, it's still true value, right? It's true value. The true value, which is actually the value we want to train, but it is noisy. Noise is deliberately introduced. Um, but this is actually a function, which is a sine wave. Okay, so now we go with a neural network architecture that we know will overfit on a sine wave. A sine wave is basically a simple second order exponential, really, right? Sine wave is e raised to power x. I think it's 1 over e raised to power x plus e raised to power minus x. I can't remember, or something like that. So but here we have if four layers, right? We have 4 layers. We have the first linear layer, and this first linear layer has one input, right, which is the value of x that we are getting, just a single dimension. And but that single input now has 128 outputs in this layer. Okay. So that gives us 256 parameters if you add the biases. Then that output 128 is passed through a ReLU and passed into another linear layer that also has 128 inputs and 128 outputs. Okay, so you can see the number of parameters now is 16,384 widths plus 128 biases. So this is 16,512. And then this is also passed through another linear layer with 128, 128, again, 128 inputs, 128 outputs, again, 16,512 total parameters. And then the final is passed through a ReLU, and then the final output is through a linear layer. Because this is a regression problem, we want to predict the actual curve. We do not use any activation function on the output. The activation function is a linear function, so that's okay. And you can see it has the 128 widths, right? Plus the one bias, which is the bias at the output. So this is the number of parameters at each, that's the number of parameters at each layer. So the total number of parameters will be to sum all of them, right? I can see that we have the 3,409, which is the sum of these numbers. Okay, so that's the overfit net. So the calculation of parameters here is not specifically correct anyway, because it's giving us something, but we know it's much more than that. Okay, so the 3,000 parameters with only 30 training samples will definitely overfit. And there's no constraint, there's no regularization, there's nothing. So we now start different training loops. So the first is the basic training loop, right? Which you can see the model is used set in train mode, optimizer is set in 0 grad. The model does a prediction. The loss is calculated with the criterion, whatever criterion that is selected. We use mean square error loss here, MSE loss, because it's a regression problem. And then we now add L1 regularization. This is optional because we want to use this training for multiple different approaches. For PyTorch, the L1 regularization is not implemented natively, so you have to manually do it. And in this case, we take the L1 lambda. Remember, the lambda is a regularization factor. And we take that factor. If it is greater than 0, that means we want to do regularization. We calculate the L1 penalty, which is the lambda times the, remember, it's the sum of the absolute value of all of the model parameters, right? So we take the parameter, we take its absolute value, right? And then we sum. And that this is basically the parameters in each layer, right? And then we sum all of that again. So that gives you also the total penalty. Then we take that penalty and multiply it by the lambda. So remember what we said, and we add that to the loss. Okay. So that gives us the loss with L1 regularization if we want to do. So this function actually helps to do two things. Normal training without L1 regularization, without any regularization, and then training with L1 regularization. Okay. So then we do the backward step, then which calculates the gradient. We do the optimizer, which is going to apply the gradients through the learning rates and all of the other parameters, depending on what type of optimizer you choose. And that increases the parameters in the model, and therefore the model learns, right? And then you remember we have to add the training losses, so we add it. Then we need to also calculate the validation losses. When you're calculating validation, you have to be in eval mode, no grad. You don't want to calculate any gradients. Just for this, more of an efficiency thing, though. It wouldn't affect the actual outcome. Okay. And then you run criterion on the model. So here, this is basically calculating a loss. Remember, criterion is what calculates a loss. We take the prediction from the model, which is just directly passing through here. We didn't need to assign it to anything. And we compare it with the actual, this is a y hat, right? And we compare it with the y hat. Okay, and we append the validation loss that's been calculated into this list. So we are keeping track of both losses, training loss and validation loss, like we said, so I can plot the graph of overfitting and see how it goes. Yeah, so we now have this useful function for plotting losses. And we have this useful function for plotting how the model fits, right? So those are all just functions. So we start off with the no regularization case. Okay. In this case, create a model, right? Um, use Adam optimizer for training. Learning rate is 0.01. Then you go ahead and train the model using the function we just wrote. You pass in the model and the optimizer. There is no L1 decay passing here, no L1 decay lambda passing here, so there will not be L1 decay applied. This will be L1 regularization. This will be standard. This will be standard training without regularization. And then we plot the model. So when this happens, you see what happens here. You actually see the model overfitting. Let me see how many epochs we had here. The number of epochs is 1000 by default, so we have 1000 epochs. And you see already, you see what's going on here. The blue is the training loss. So initially you can see that the test of validation loss was even lower. But as you keep training, it comes up and then it crosses this line. At this point, it begins to overfit. And it just continues to go that way while this training keeps going down. And there are even spikes here. These spikes are also really bad for the model, right? So at the end of the day, the orange line here is what the model predicted. And you will see how the model is basically fitting every single value, every single noise in the data set, right? And it's too far away from what we want. The real curve is this, where it is following the trend rather than following the noise. So that's without overfitting. Now we apply L2 regularization, which is weight decay. So for weight decay, Torch allows you to do it easily. You don't need to really do that calculation yourself, even though you could have done it, right? We put in a calculation to do L1, but Torch doesn't give you that capability to do L1 on your own. You have to add it, insert into the training loop. But for L2, Torch adds it to the optimizer. So um, when you are creating the optimizer, after you've created the net, when you are creating the optimizer, okay, you can specify the weight decay. And when you specify the weight decay, the value you specify is a lambda actually specifying, which in this case 5e raised to power minus 3 is 0.0005. So there are different values we can try out here, right? But this was what was used. And of course, you can see that we trained the model and we got the training and validation losses. So we now plotted everything again, and then plotted the fits. So here you can see that regularization actually helps. You can see that it does not overfit. The validation loss actually just drops seriously and stays there. But it keeps staying below the training loss. The training loss flattens out. So you can even see that here, I didn't really need so many epochs to train this model. It's a simple sine equation. So this was for demo purposes, right? But typically, you wouldn't even need, you don't need more than a few epochs to fit into a sine. But even at that, you can see that there's still a bit of overfit here, right? It's not as bad as the other one, but it's not really giving us a sine wave, though it's close to it. This is L2 regularization. Now, same thing here with L1 regularization. Now we are doing manual, so we'll pass in the um or we'll do the Adam again, right? Um we use Adam all through here. We didn't use SGT, but I'll give you a task where you can try it out with SGT, see what happens. So this time around, we trained the model, but here we specified it. So remember, L2 was specified in the optimizer because optimizer gave us that capability as weight decay. But um, in L1, we have to pass in the lambda, which is 1e minus 3 this time around. And you can also see what it plots. So with L1 regularization, it does um, kind of, yeah, same thing, right? By the way, if you're asking why is the training loss or why the validation loss lower, it's because there's no noise. The validation loss doesn't have any noise in it. The training validation data doesn't have any noise in it. So it will predict it with higher accuracy. But the training data has a lot of noise in it. Okay. So yeah, you get kind of same thing, almost same thing as what you got with L2 regularization. Then dropout, in dropout, for you to implement dropout, there's actually a layer called dropout layer, right? So instead of you manually coding in when to drop out some neurons and so on, what you just do is in your architecture here, so we have to use a different architecture, but everything is the same except that we introduce two dropout layers. Dropout layers are normally introduced at the input to a new layer, right? Or output from a previous layer. So here, at the input to this linear layer and the input to this other linear layer. So that at that input point, you specify the probability of dropout, which in this case 0.5. That's 50% probability. So it means that there's a probability that neurons will be dropped with 50% probability, right? It doesn't mean that 50% of neurons will be dropped, by the way. It doesn't mean that 50% of neurons will be dropped, but it means that a neuron will be dropped or some neurons will be dropped with a probability of 0.5, 50%. Okay. So you can go learn a bit more about drop dropout. Okay, so dropout is an architectural change that requires um, you to adjust the model. But yeah, with that, when you do dropout, then you train the model as usual. You don't put any other regularization, right? The dropout itself is the regularization. So you don't put any other calculated regularization or anything. And you can see the model, the training loss is so noisy. And the reason why it's noisy is the dropout. The dropout makes it, when you drop out one neuron, the loss will change, right? And then you drop out another neuron, the loss will change. So the loss is not stable like before. It actually keeps jumping around. Even the validation also keeps jumping around, but to less extent. Okay. Now with dropout, you see that dropout actually comes even closer to the sine wave, which is quite interesting, right? Dropout is learning the real pattern and not all that noise that we have added. Then um early stopping. So we talked about early stopping as well. Early stopping is basically still the same net. This time around we did a new training loop. We added early stopping. And the early stopping here is after you do your validation loss, you do your training, you already have your training loss, do your validation loss. You now check if the validation loss is lower. So when the validation loss stops dropping and begins to increase, then you increase this patience counter. And once the patience counter gets to the value of the patience that you passed in, then you trigger early stopping, basically, and you stop, you break out of the training loop, right? Of course, you have to ensure that you keep track of the losses, training loss, the validation loss. But more importantly, you have to keep the model that had the best performance, right? That's what this is doing. This is how you extract state, the parameters. The parameter is part of the state in PyTorch. So for you to save the state, you use model.stateDict. The return value from there, you can save it somewhere in a variable. You can even save it on your file system so that if you want to continue the training tomorrow, you can load that state dict. We'll talk about that later. You can load it and use it to initialize the model. You even see it here. Okay, so yeah, early stopping. So this is where you load it, right? You have to restore the model to the best loss. Since the best state was stored here, you now use model load state dict. So load state dict is going to load the parameters that you trained to that had the best performance and all the states. And then we plot it, right? And you can see how early stopping works. So this time around, you can see all these other approaches. The most telling difference here is that all of them trained to 1,000 epochs because there was nothing like early stopping or any kind of you know, schedule time, basically time management. But with early stopping, it got to 80 epochs, right? But the best epoch is at 34. So the question is, if the best epoch is at 34, why did we continue training to epoch 84 before breaking out? Because our patience value is 50, meaning that we want to train for another 50 epochs just to be sure that I cannot get a better model. And because we are tracking the best model, we can restore to the best model after the training. And you can now see that the best model from early stopping is almost the same thing as the models that we got from L1 and L2 regularization. So that is a summary of regularization and the effects. I'm going to share this notebook so you can also go through it. And this is a summary of it, right? Yeah, that's all from me. Are there any questions?